The IDR 300 spectroradiometer is composed of two single 300mm focal length monochromators operating in tandem with additive dispersion to yield a 600mm double monochromator, with the option using an exit slit on the first monochromator as a single monochromator use. The optical layout of the IDR 300 is as follows. I have removed the lid of the IDR 300 spectroradiometer to allow viewing its optical layout. We recommend that you never remove the lid for two reasons. One, to ensure that no dust and other contaminants get within the space of the double monochromator, and secondly, for a fear that were one to touch any of the optical elements, only damage can occur. It is not possible to clean, for example, fingerprints. As we have seen, the IDR 300 double monochromator is composed of two single 300mm focal length monochromators operating in the Czerny-Turner configuration, the symmetric Czerny-Turner configuration, and they work in tandem with additive dispersion to give us a 600mm focal length double monochromator. In each of the component single monochromators is located a turret which is stepping motor driven, to which up to 3 diffraction gratings may be mounted. And we can see here in the first monochromator 3 diffraction gratings are mounted, and here in the second monochromator there are only 2. At the exit of the first and second monochromators are located solenoid-based mirrors, swing-away mirrors, or SAMs, which can either come into the beam as here to reflect light to the second monochromator in this case, or they can move out of the beam to allow light to go straight to the exit slit. As in here, light would go directly to the exit slit of the first monochromator, and here light goes to the exit slit to the rear, and with the SAM in place, light would be relayed to the exit slit to the right. So we have a single monochromator mode, 1 exit port, and double monochromator mode has 2 exit ports. Behind the entrance slit is located an order sorting filter wheel, and entrance and exit ports, 1 entrance port and 1, 2, 3 exit ports, are fitted with motorized slits which are controlled through computer. So looking at what happens to light instant on the monochromator, firstly it's reflected by a plane mirror towards a spherical collimating mirror which has a 300mm focal length and is located 300mm from the entrance slit, so the distance from here to here. And as a result, light is collimated towards the diffraction grating. Light instant on the diffraction grating diffracts, and then the diffraction from all of the grooves on the diffraction grating interferes, and we have dispersion to the component wavelengths, and we can see the first order on either side of the diffraction grating. So the dispersed light is made to be instant on a spherical collimating mirror, the same as the first, having 300mm focal length, and again 300mm from the exit slit. And in this manner, the dispersed light is imaged onto the plane of the exit slit, of the first exit slit, if the swing-away mirror is out of the way. Otherwise, with the swing-away mirror in the beam, light is relayed to the second monochromator. And the grating rotates, and we select the wavelength, measure, and rotates, measures, and there we go. In the single monochromator mode, the swing-away mirror would, as opposed to this image, be out of the beam to allow light to go to the exit of the first monochromator. Now, one concern with the use of single monochromators is that of stray light. A monochromator is effectively used as a filter. It's used to select a given wavelength, a desired wavelength. Now, if, for example, any of the input light overfills the mirrors and is therefore reflected into an arbitrary direction, or if there are any contaminants in the mirrors and diffraction grating, or defects on the diffraction grating, then light may be scattered within the area of the monochromator. As a result, what we find is at the exit port, not only do we find the selected wavelength, but some level of effectively white, broadband, scattered light, stray light. Now, in many cases, this is of little import. For example, we're one to measure a source emitting lots of visible light, but very little UV light, and one wants to measure in the UV. Then one finds that the stray light component may be higher than the actual UV component one is trying to measure. And it's for this reason that we should look towards the use of double monochromators. So in a double monochromator mode, the swing away mirror relays light to the second monochromator. The process is repeated. Light is further dispersed by the diffraction grating and then presented either to the right hand or rear exit ports. In this manner, we reselect the wavelength desired. We effectively select from the stray light presented to the second monochromator the wavelength desired, and we have again some very low level of stray light. The stray light performance of the double monochromator is very significantly greater than that of a single monochromator. In the IDR 300 PSL, we have the following diffraction ratings: 2400 grooves per millimeter in both monochromators for 200 to 320 nanometers, a 1200 line diffraction grating in both monochromators for use up to 1100 nanometers, and then to cover the infrared region, we only use the single monochromator with the first monochromator exit slit to cover the range up to 3000 nanometers. We can see the diffraction gratings have blaze wavelengths, or wavelengths at which the performance is optimized in the UV, visible and infrared. It's worthy to note that the higher the line density, the more light is dispersed. So we can see, for example, we have 1.35 nanometers per millimeter for the 2400 line grating, but very many more nanometers per millimeter for the infrared grating. This is important to take account of when one is performing a scan over a wide spectral range and one wants to maintain a given bandwidth, for example, so that we need to, as we change diffraction gratings, modify the motorized slits. Behind the entrance port of the IDR 300, we have a stepping motor driven order sorting filter wheel, which is fitted with the OS 400, OS 700, OS 1250 and OS 2000 nanometer long pass filters for the purposes of the suppression of higher diffraction orders. And we also have a shutter fitted, which allows for the measurement of the dark current of the detectors and the offsets of the detection electronics. The entrance and exit slits are fitted with stepping motor driven motorized slits. These motorized slits have a fixed height and a variable width. We have seen for the diffraction gratings of the system, we have a different dispersion in both the single and double monochromator mode and for each grating. If we were to take, for example, a measurement that we want to step in 5 nanometers and maintaining the system in 5 nanometer bandwidth, we see that the dimensions of the slit varies throughout. And this is controlled through the software in measurement dynamically. As we go through the measurement range, the slits will adjust as required. This, of course, when in Bowman Plus Instruments menu, the motorized slits are set to the auto mode, in which case the slits will be set to the same as the step size employed. In the DC configuration, the following detectors are mounted to the IDR 300. To the exit of the second monochromator in double configuration is a DH3 multi-alkali photomultiplier and a DHSI silicon photodiode, whilst to the exit of the first monochromator in the single monochromator mode is a DH-IGA3 lens InGaAs photodiode. The DH3 comprises an S20 photocathode photomultiplier. This benefits from electron gain, so for a low signal input we have a high measurable current. And this is the ideal measurement detector for measurements in the UV, for example, and in measurements of irradiance. After 850 nanometers or less, the response of this detector goes to naught, and we have to migrate by moving a swing away mirror out of the beam to allow light to the silicon photodiode. A simple PIN junction, the silicon photodiode does not benefit from the electron gain of the PMT, and as such has a very much lower response. We can, however, use this to our benefit in measurements where, for example, the signal level would be too high for the photomultiplier, such as the radiance measurement in 11 milliradians and high radiance mode, in which case the photomultiplier is used to 400 nanometers, thereafter the silicon photodiode is used. The difference in the responsivity of the two detectors also explains the jump that is seen when calibrating the system and having a high signal from the photomultiplier to 850 nanometers in the irradiance configuration, for example, and then the very low response from the silicon photodiode. After 1100 nanometers, at the end of the range of silicon, we no longer use the double monochromator configuration, and we migrate to a single monochromator configuration by moving a swing away mirror at the exit of the first monochromator out of the beam, allowing light to go to the InGaAs photodiode. Again, a PIN junction with no electron gain. The InGaAs photodiode responds from 800 to 1700 nanometers. In this manner, we can say that in its base configuration, the IDR300 can be used from 200 to 1700 nanometers. However, in the measurements that we will perform in the typical configuration, we will only use this configuration up to 1400 nanometers and then migrate to the IR setup for measurements to 3 microns. The IDR300 comprises 2 transimpedance amplifiers followed by A to D converters and a HV supply. The HV supply being required for operation of the electron gain in the photomultiplier, and is also used in the infrared to operate the lead sulfide detector, which is used in the photoconductive mode. The 2 amplifiers have 2 inputs. 2 inputs to the first amplifier to measure the signal from the photomultiplier and the silicon photodiode, and the 2 inputs from the second amplifier measures the signal from the InGaAs photodiode and the last from the photometric detector, which is part of the virtual lux meter to determine 500 lux distance. The IDR has a mains input and USB input to the front. The IDR300 is fitted with motorized slits at the entrance and exits, all operated in tandem to the same dimension. Entrance exit slits define the system bandwidth, how many wavelengths are seen at a time. And clearly, the lower the bandwidth, the higher the spectral resolution, but the lower the throughput, which is a very important aspect to consider. The IDR300 PSL has been configured to operate with regards to the requirements of IEC and EN 6471, with recommended bandwidths for use of the PSL system of 2 nanometers between 200 and 400 nanometers, and 5 nanometers up to 1400 nanometers, whilst in the infrared 10 nanometers is employed. This short video has been included to show the importance of following the advice with regards to the installation of the FOP UV fibre bundle to the entrance port of the IDR300 spectral radiometer in the spectral check, irradiance and radiance configurations. The IDR300 is fitted with motorized slits to define the system bandwidth. The motorized slits have a fixed height and a variable width around a central point. In the IDR300 PSL system, we operate the slits in an auto mode. In this manner, the system bandwidth is set to be the same as the measurement step size. Since in many instances we will change the step size through the measurement scan, for example having a 2 nanometer step in the UV and 5 nanometers thereafter, the slits will change to adapt to the change in bandwidth. Furthermore, as one migrates from the 2400 line per millimeter diffraction grating to the 1200 line per millimeter diffraction grating to the 400 line per millimeter diffraction grating, each of which has a different dispersion, the motorized slits must change their dimensions to account for maintaining the system bandwidth. When one performs a scan, at the end of the scan, the motorized slits are left in the open position. As can be seen here, the central black region corresponding to the area through which light is transmitted to the monochromator. When one initializes the software, the motorized slits are closed to a datum position. And with respect to this datum position, the dimension of the slit is set for a given bandwidth required and a given grating in use. One should note that, as we can see here, we have to either side of the central point the slits, the jaws that define the bandwidth, and to the left and right of these, brass blocks, which are supports for the slits. The distance between these brass blocks is 8.4 millimeters when the slits are closed. And now we will look at the fiber bundle which we wish to install in the slit. Now we will look at the fiber bundle. Whilst the FOP UV fiber bundle has a round fiber formation at the entrance optic side, on the side of the fiber bundle intended to install to the IDR300, the fibers are formed in a rectangular form to match the entrance slit of the monochromator. The metal ferrule of the fiber bundle has been designed such that the fibers can go as close as possible to the slits of the monochromator to lose a minimum of light. The lateral dimension of the top part of the ferrule is 8 millimeters, whilst we have said that the distance between the brass blocks within the motorized slit is 8.4 millimeters. With the slits closed, one can successfully push the fiber in and engage it between the brass blocks. And this is the correct way to install the fiber using the grub screw to hold the fiber in place. Where the entrance slits are open, for example at the end of a scan, there is scope for one to position the fiber and that the fiber be at an angle. Effectively, one can rest against the brass blocks, for example, and their open position as an extreme case. If one were to do this and hold the fiber in place with the grub screw, the next time one wishes to initialize the software, the slits will attempt to close, but the fiber will block the brass blocks from closing, and a most terrible sound will be heard, which may cause damage to the slits. In all instances, where the fiber has already been installed correctly and one goes from my configuration to configuration, one need to take no further action. One just leaves the fiber installed. Where one comes to the system and the fiber is not connected, in all cases, first please initialize the software. Have the slits closed, wait to the end of the procedure, and then, and only then, can we fit the fiber bundle, with confidence that the orientation of the fiber bundle will not impede the motorized slits from closing. The monocreaser is finished. Its motion, we fit the fibre bundle in as close as possible. Very little of the fibre bundle ferrule remains exposed, and we hold in place with the grub screw.